Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is Chemical Thermodynamics, Advanced Heat Capacity and Internal Energy. These concepts are not only crucial for understanding how energy flows in a system but also play a significant role in solving complex numerical problems. So, let's get started. Thermodynamics deals with the study of energy changes that occur during physical and chemical processes. It provides us with a framework to understand how heat, work, and energy interact and transform from one form to another. Among the various concepts in thermodynamics, heat capacity and internal energy are fundamental in understanding the thermal behavior of substances. Let's start by understanding heat capacity. Heat capacity is a measure of the amount of heat required to raise the temperature of a substance by 1 degree. It tells us how much heat energy a system can absorb without experiencing a significant change in temperature. The heat capacity of a substance depends on both its mass and its specific nature. When we talk about heat capacity, it's important to distinguish between two types: heat capacity at constant volume and heat capacity at constant pressure. These two scenarios are essential because the behavior of gases, liquids, and solids changes depending on whether the system is allowed to expand or not. If the volume is kept constant, all the heat supplied goes into increasing the internal energy of the system. This is because no work is done by the system during expansion or contraction. In this case, the heat capacity is referred to as heat capacity at constant volume. Since the volume remains unchanged, the heat supplied increases the kinetic and potential energy of the particles within the system. On the other hand, when the system is allowed to expand at constant pressure, some of the heat supplied is used to do work in addition to increasing the internal energy. This is known as heat capacity at constant pressure. Because the system performs work against the external pressure while expanding, the heat required to raise the temperature is greater than that at constant volume. The difference between heat capacity at constant volume and heat capacity at constant pressure becomes more pronounced in gases. This is because gases have a higher degree of freedom, allowing them to move, rotate, and vibrate. These additional degrees of freedom influence the amount of heat required to increase the temperature, making heat capacity an essential parameter in understanding the behavior of gases. Now, let's shift our focus to internal energy, another critical concept in thermodynamics. Internal energy is the total energy contained within a system. It includes both the kinetic energy due to the motion of particles and the potential energy arising from the interactions between them. Internal energy is a state function, which means it depends only on the initial and final states of the system, not on the path taken to reach those states. The internal energy of a system can change in two ways: by adding or removing heat, or by doing work on or by the system. When heat is supplied to a system, the kinetic energy of the particles increases, leading to a rise in temperature. Similarly, when a system performs work on its surroundings, some of its internal energy is used to do that work, causing a decrease in internal energy. One of the most important aspects of internal energy is its relationship with heat and work. This relationship is described by the first law of thermodynamics, which states that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system on its surroundings. This fundamental law provides the basis for understanding how energy is conserved in all processes. Heat capacity is classified into two types based on the conditions under which heat is supplied: heat capacity at constant volume and heat capacity at constant pressure. At constant volume, no work is done since the volume remains unchanged, and all the heat supplied goes into changing the internal energy of the system. This is particularly significant in studying gases in closed containers where expansion is restricted. On the other hand, at constant pressure, the system is allowed to expand, meaning that some of the heat supplied is used to perform work against the external pressure, while the rest contributes to changing the internal energy. In the context of gases, the change in internal energy is directly related to the heat capacity at constant volume. Since no work is done at constant volume, all the heat added goes into increasing the internal energy of the gas. However, when the gas expands or contracts at constant pressure, a portion of the heat is used to do work, and the remaining heat contributes to the change in internal energy. Understanding the concept of internal energy is essential for analyzing various thermodynamic processes such as isothermal, adiabatic, and isobaric processes. In isothermal processes, the internal energy remains constant because there is no change in temperature, while in adiabatic processes, the internal energy changes as heat is neither gained nor lost by the system. The interplay between heat capacity and internal energy helps explain how substances respond to changes in temperature and pressure. For example, when a gas is compressed, its internal energy increases, causing a rise in temperature. Conversely, when a gas expands, its internal energy decreases, resulting in a drop in temperature. These concepts are not just theoretical but have numerous practical applications. Heat capacity is used in designing heat exchangers and engines, while the understanding of internal energy is crucial in predicting the behavior of gases in industrial processes. Thermodynamics also plays a significant role in environmental science, where heat capacity helps us understand how oceans and the atmosphere regulate Earth's temperature. To put it all together, heat capacity determines how much heat is required to change the temperature of a substance, while internal energy accounts for the total energy stored within a system. Mastering these concepts will not only strengthen your understanding of thermodynamics but also equip you to tackle numerical problems with confidence. That's it for today's session on chemical thermodynamics. I hope this detailed explanation has clarified your doubts and enhanced your understanding of heat capacity and internal energy. Thank you. We hope this video has helped you gain a clearer understanding of hydrogen and its compounds, especially the fascinating role of heavy water and isotopes. If you found this video helpful, make sure to like, share, and subscribe to AskPrep for more in-depth chemistry lessons. Keep studying, stay curious, and good luck with your exams.